Last time we started talking about scheduling systems. We said that no process can, really any process can keep the CPU very busy all the time. They need to have some kind of a CPU usage area, like a CPU burst, and they would block. Then another CPU burst, and they would block. Sometimes they do this very often, like in this case. Sometimes their CPU bursts out for a longer time. It doesn't matter. For both of these cases, we need scheduling algorithms just to decide which process should take over the CPU when one of the processes are blocked or it is using too much CPU. And this is called scheduling. And we talked about it a little bit. Several processes are runnable, and which one should we run next? And many different ways to make this decision. We talk about those, and I will go faster now because I already talked about those. One important thing in the scheduling algorithm is the preemptive algorithms versus non-preemptive algorithms. Preemption means that even though the process can still continue using the CPU, it is not blocked. Operating system might decide that it used too much CPU time and it preempts the CPU and let another process use that CPU. So this is called preemption. Okay, switches after a time quantum. After a process uses the CPU, we said, okay, it is enough. Now some other process is going to use it. This is called preemption. Suspending a process without process being blocked. Okay, so we are going to look at the scheduling algorithms in three different categories. Batch systems, those old systems from 1960s, or even today there are some batch systems and they need some scheduling algorithms. Interactive systems like the PCs, and the real-time systems or soft real-time systems like the power plant controller or the medical device controller or the car computer. These are all real-time or soft real-time systems. They are usually non-preemptive because they process around very short amount of time, and they don't need to be suspended unless they need some kind of an I/O. Okay, so let's continue. We said that there are a few criteria for all the systems, whether they are batch systems, interactive systems, or real-time systems. The schedule must be fair. Okay, give each process its share of the CPU. Policy and enforcement, it depends on the environment. For the batch environments, CPU utilization is something very important because for the batch environments, CPUs are very expensive. But for the interactive environments, it's not the CPU utilization, but it is the user satisfaction. And for the real-time systems, it is the meeting of the deadlines. So the policy and enforcement is different for different kinds of systems. And the balance, keep all parts of the system busy so that we are using our computers efficiently. Batch systems, throughput, turnaround time, and CPU utilization is important for batch systems, and we will talk about this in a little bit. For interactive systems, response time and meeting the user expectations. Cheap request, finish quickly. What is cheap request? We talked about this last time. Cheap request. mouse movement is like a cheap request, yes. I mean, there is no very perfect definition for the cheap request, but cheap requests are the requests that the user thinks that they are very easy to implement, okay? Like when I move the mouse, I would think that this is a very, very cheap in terms of CPU usage request, so it should be completed in a small amount of time. But if I am uploading a 2 gigabytes of video to YouTube, it should take half an hour, right? So I don't expect uploading 2 gigabytes of video to YouTube in a few seconds. Those are expensive. So that's the user perception, user psychology. Okay. So operating systems has some things to do with the human psychology. Everybody wants their job to be done in a very short amount of time. That's the interactive system. The scheduler should pay attention to this kind of criteria. For the real-time systems, meeting the deadline, predictability, and always doing the things on time is important. So when the time comes, we will look at these later. Okay. So let's look at these batch schedulers. Remember, in the batch schedulers, what was the important thing? Throughput. Okay. CPU utilization and turnaround time. These are the important things, and we are going to look at these three batch schedulers. First come, first served. This is the first scheduler ever invented. It is really so easy. So if you have a few tasks to be completed by the batch system, okay. If task A came before B, then it came C, then E. So A is run first, then B, then C, then D. So first come, first served. That's as simple as this. Okay, as simple as this. If A blocks for some I/O operation, then you let B run, and B blocks, then you let C run, and then D runs after that. So this is the no preemption with the batch systems actually. For the batch schedulers, usually we don't use any preemption, because preemption is good for stopping processes that takes too much CPU time in a single CPU burst. But for these cases, since we don't have any interactivity, your job runs for 10 hours. Okay, all of these A, B, C, D, you need maybe 24 hours for all of them to finish. So I don't need any interaction. That's why usually we don't use any preemption with the first come, first served systems. It seems simple. It seems simple, but there are some not very fair problems with this approach. Actually, I had a few additional comments on that one. I wonder what happened. Didn't I? Okay, let me see. Okay, that's important. That's okay. Let me say that not very fair. I mean, first come, first served looks like it's fair, but in some cases, let's say CPU A is doing process A is doing this. Okay, A is doing this. B is doing this. Okay, A and B. So when we do this first come, first served thing, A will get much more CPU usage time than B, C, D, and E. Right? Because these are the CPU burst times for the B, C, D, and E. These other four processes. Why? Because A takes the CPU, it runs this much of time. Okay, it times for a long time. And when it is blocks, B is run. When B blocks, C is run. Then D blocks, then D run. Then D is run. Okay. Then we come back to A, and A runs after that. Okay. So as you see, A, B, C, D, E, they are all processes, but most of the time CPU used by the CPU is used by the process A, which is not fair for the B, C, D, and E, because since they have a very short amount of CPU burst time and they would block immediately, once they block, they have to wait for A to finish its job with the CPU. But A takes so long time, they have to wait. So while A is using most of the CPU, B, C, D, and E, since they have this structure, they are not using CPU enough. So what is the bad side of this thing? This way, our throughput is getting lower and lower, because instead of finishing these jobs B, C, D, and E on time, I am giving more importance to A. So B, C, D, and E will get late to finish their jobs, and so the overall throughput will be smaller. That's why we say that first come first serve. It is not always very fair, especially if one of the processes are CPU bound. Okay, it is using several CPU intensive tasks. Okay, so this was the first batch system scheduler. The second one is they are doing this. Okay, in the batch systems, let's say I have 4 processes A, B, C, and D. Okay, A, B, C, and D, and we know how long they are going to take. How do we know how long they are going to take in the batch systems? A will take 8 seconds, B will take 4 seconds, C takes 4 seconds, and D. B, C, D, they all take 4 seconds to complete, and A takes 8 seconds. How do you know that they will take this much? Remember, this is a batch scheduler system. Since it's a batch system, well, give me an example for a batch task. Calculation of the interest rates. Calculation of the interest for the bank accounts, right? Let's say I have a million bank accounts, and calculation of the interest for the whole bank accounts will take 8 hours. How do I know that? Because last time I ran it last month, it took 8 hours, right? So in the batch systems, you would know how much time it will take. So I know each of those will take. So the problem here is that if I use first come, first served, okay, first come, first served, how long would it take to complete all these tasks? It would take 12 plus 20 seconds, right? It will take 20 seconds. If I change their positions, if I do it this way, will it take any shorter? No, it will take 20 seconds again. But what would be the difference? The difference would be the wait time for these B, C, D jobs. In that case, B, C, and D have to wait. All of them, okay, have to wait for this A to finish, right? So in order for B to finish, it will take 12 seconds. For the C to finish, it will take 16. And for the D to take, it will take how many? 20 seconds, right? So overall, in that case, 8 plus 12 plus 16 plus 20 over 4. Okay. This is my throughput. Okay. This is my turnaround. This is my turnaround time. If I do it that way, this would be my turnaround. Turnaround means that average job completion time, right? So what is the turnaround time here in this case? It is 20, 40, 36 over, is that correct? No, 20, 40, 56, right? 20, 40, 56 over 4, right? So it is 14. 14 seconds. 14 seconds is my turnaround time. But if I arrange it this way, it would take 4 seconds for B, right? 4 seconds for B, then 8 seconds, then 12 seconds, then 20 seconds over 4. How about this? What? 11. Okay, 1, 2, 3, Okay. 14 versus this is 14. This is 14. One and 4. This is 14 and this is 11. So as you see, when you change the order of the jobs, my throughput, my turnaround increases. My turnaround increases. Throughput is the same. It is, I mean, 4 tasks for 20 seconds. So that's my throughput. But the turnaround time, the average turnaround time is 11 seconds for this one. So we would say that if you bring the shortest jobs at the beginning of the queue, okay, it's not the first come first serve now. It is the shortest first. Okay, shortest one is taken first, and that will increase my throughput time. Okay, so that's the formula actually. You understand this formula? How did they get this formula? 4 times A plus 3 times B plus 3 times C and plus. Where did you get this formula? This is the formula for the first case, right? This is the formula for the first case. A, B, C, D. Okay? So why this is 4 times A? It is 4 times A because the last task has to wait for A to finish, right? I mean, and the second task it needs it to finish, and the third one, and the last one, and the first one. So for each task, A has to finish, right? For each task, A has to finish. So it increases my turnaround time. They say that if I am multiplying A with 4, then A should be the shortest one, B the next, then C next, then D should be the slowest or the longest task that I should run. Okay. So this is the shortest first scheduling algorithm, and an improvement over the first come first served algorithm. Okay, any questions so far?
Turnaround'un ne olduğunu da
Efendim?
Turnaround time'ın ne olduğunu.
Turnaround time is the average job completion time for each of these processes. Average job completion time. So it takes me, in that case, for each job, in that case upstairs, A takes 8 seconds, this one takes 8 plus 12, it takes 12 seconds, this one takes 16, and this one takes 20 seconds, okay? So I add them up and divide them by 4 because I have 4 jobs. So each job takes 14 seconds on average. But in this case, each job takes 11 seconds on average. So the total completion does not change. Okay, my throughput is the same. Okay, my throughput is the same, but mean turnaround time is important. Mean turnaround time is important. Remember, we had that for the batch schedulers, we had the turnaround time, throughput, and the CPU utilization, right? 3 important things. For the turnaround time, I can't do anything. For the throughput, I can't do anything. But for the turnaround time, I can make this improvement. Okay. Any other questions? Where is the attendance? Attendance sheet. Okay. Okay. Then the thing is that most of the time I don't receive all the jobs at the same time. Okay. Jobs come while I am running them. Okay. So jobs don't arrive at the same time. So I can't make an optimal scheduling decision without complete knowledge. I mean, in this case, it is easy to make the optimal scheduling decision because I know all the jobs and I know how long they are going to run. But if I don't have all the jobs in front of me when I started running, then I cannot make decisions. For example, I have these jobs. The first job, A, let's say A will take 2 seconds, B, C, D, and E. Okay, A, B, C, D, and E. A take 2 seconds, then 4, then 1, and then. I mean, if I have all of these 5 in front of me, then I would say that run C, D, E first, then A, then B, right? But it says that these jobs arrived at time 0, then at time 0, this is A arrives at time 0, B arrives at time 0, and C and D and E. So in that case, I wouldn't know the perfect or the optimal schedule because I don't have all the data with me. Okay, so the shortest first runs average is 4.6 seconds. But if you run BCDE, it drops down to 4.4 seconds. But I can do this without knowing which one will come next. So that's the downside of the shortest first algorithm. Okay, shortest first algorithm. It is not easy to get all this data, the running times and the which one is going to run next at the same time. That's what we are seeing. Okay. Another improvement or the first come first served is the shortest remaining time next. Okay. So this is the preemptive variant of the first come first served. We are using a preemption now in the batch systems. It's the preemptive variant of the first come first served. Shortest remaining time is this. I need to know what each process, how long each process will take. Okay, that's one thing I need to know. And the other thing is that if I have a new process coming in, I can preempt the running process and let the new process run if it is going to take shorter time. Okay, so it helps me in getting the short jobs to get good service. In this case, when process A or B is running, if I receive this process C and I would know that it would take 1 second, then I can preempt A or B and let C run. Okay, let the process C run. So that's called shortest remaining time next. It's a preemption version of this first come first served or the shortest time, shortest first algorithm. But we need to use preemption. If I get a new job, then I need to preempt the running job if it's going to take shorter.